All engineers aspire to design structures that never fail, but unfortunately structures tend to fail under stress and loading. When a structure is placed under some load, it experiences a stress. Every material has a unique material property called ultimate stress. When a structure experiences a stress greater than its ultimate stress, it fails. Because these structures are not only a matter of convenience, but also important to people's safety, the structures are designed to have an allowable stress that is less than the material's ultimate stress by a factor of safety. As engineers, we try to design a structure so that the maximum stress the structure experiences does not exceed the allowable stress. This makes sure that the structure does not fail during its intended use. This is why it is crucial to study stress concentration as well as distribution of stress within a structure. In this lab, we studied stress concentration using a thin polycarbonate plate with a hole in the center. Here you can see the shape of the plate that was used in the experiment. Uniaxial loading along the length of the plate was applied on the plate. The HH line cuts across the cross-section with the minimum area. For prismatic materials placed under uniaxial loading, we would calculate the stress by dividing the applied force by the cross-sectional area. However, in this case, we also need to consider the stress concentration factor, K, because there is a hole in the plate. The plate has a width of 10 inches and a hole radius of half an inch. The thickness of the plate was 211 thousandths of an inch. Before testing the material with the Instron machine, we used MATLAB to predict the stress distribution along the HH line. This graph shows the stress in the plate as a function of distance from the center of the plate. Right at the edge of the hole, half an inch away from the center, the stress is the greatest at about 3,000 psi. As the distance from the center of the hole increases, stress decreases. This shows that stress is much more concentrated around the edge than further away from the center. Stress drops off significantly at first, but asymptotically approaches an average stress at about 1,000 psi. The maximum stress is approximately 3 times the average stress. This makes sense because when the radius of the hole is small relative to the width of the plate, the stress concentration factor is about 3. Next, we use SOLIDWORKS to run a finite element analysis to simulate the loading and the stress distribution within the plate. We only used a quarter of the plate because the plate is doubly symmetric about the center. The first thing we did was to create a mesh. Notice the increased concentration of nodes around the hole as opposed to the less concentrated nodes in the rest of the plate. This is because stress is more uniform in the rest of the plate and much more concentrated around the hole. So it was unnecessary to make the mesh equally fine throughout. Different colors represent different magnitudes of stress. The legend shows this as a scale using a spectrum of colors, red being the highest stress and blue being the lowest. The results of the analysis correspond to the MATLAB predictions. Along the HH line, which is the bottom edge of the model, the stress is at a maximum value right at the edge of the hole and decreases with distance from the hole. The maximum stress is about 3 times the average stress, which again agrees with our MATLAB prediction. This video shows a simulation of the uniaxial loading and unloading cycle that was later conducted using the Instron machine. Recall that blue corresponds to the minimum stress, which in this case corresponds to when the applied load is 0. So, when the entire plate is blue, there is no load applied on the plate. As load is applied, the stress concentration appears around the hole. The polycarbonate plate was loaded in the Instron machine using supports at the top and bottom of the plate. A screen that emits polarized light was placed behind the plate. This lit screen enabled us to see the stress concentration in the plate by passing polarized light through the plate. A Nikon DSLR and a Sony camcorder with polarized filters were then used to capture the photoelastic visualization in photos and video, respectively. 10 strain gauges were attached to the plate along the HH line to measure the strain. Before any load is applied, there are no stress contour lines within the plate. This agrees with our SOLIDWORKS simulation when the model was entirely blue and there was no stress buildup in the plate. As the load increased, the stress concentration slowly accumulated around the hole. Also, you can see that the stress concentrations do not change as drastically further away from the hole as near the hole. This image shows the plate when it is fully loaded with 2,000 pounds of tensile force. Denser contour lines indicate higher values of stress. On the HH line, the contour lines are most densely packed at the edge of the hole. As the distance from the hole increases, the stress distribution becomes more uniform. This matches our finite element analysis simulation shown earlier. As the plate was unloaded, the density of the contour lines around the hole decreased. The unloading of the plate is essentially a reverse process of the loading. We can see that at the end of the unloading, the plate had gone back to its original state, where both stress and strain are zero. This is because the material remained in its elastic region during loading. This means the maximum stress experienced by the plate did not exceed the yield stress of the material, and there was no plastic deformation. The Instron machine also showed that the material behaved linearly throughout the entire process, indicating that the proportional limit was not exceeded either. The data collected using the strain gauge was analyzed using MATLAB. We plotted a stress distribution graph using the experimental data. The trend shown on the plot resembles the trend demonstrated by the prediction made earlier using MATLAB. From this lab, we learned that distribution of stress within a structure is greatly affected by its geometry as well as different features, such as holes or fillets. It is often necessary to introduce different features to a structure. As engineers, as we put these features into our designs, we must always consider the stress concentration that arises from these features so that we can design a structure that is not only functional but also durable.